All right. Hello, class. This is a lesson for IB Physics HL. I have fixed some things so that I think you should be able to do the live chat. And so I'm just going to monitor the live chat if you have any questions. I don't know how much of a delay there is, but if I see a question on the side, so I'm not going to check my phone. I said I was going to check my phone, but I figured out how to do the live chat, so I'm going to do that instead. This is for the IB Physics HL students, and today's lesson is going to be about the Doppler effect. This should be a quick one. And by the way, IB Physics HL students should IB Physics HL students should also watch the AP Physics C video if you can. So this is, I intended to teach you guys this on Friday, but we just we set up the distance learning on Friday instead. Okay, so you might remember so what is the Doppler effect? So let me just tell you what it is first. It's a shift in the observed frequency of a wave when the source and the observer are in relative motion. Okay? So it's a shift in the observed frequency when the source and the observer are in relative motion. So you all know about, the sound, the Doppler. If there's a Doppler effect of sound, it plays with the frequency of sound. So it plays with the pitch of sound. Oh, we got a question from Zach. It says, is the stuff from the APC lecture on the IB test? Not on this current test that I'm going to give you guys soon, but it will be on the next one. So it'll be on next week's quiz. Okay? Which I encourage you to collaborate. You can collaborate as much as you want. Okay, so if it's the Doppler effect with sound waves, you're going to hear a shift in pitch. So, you see when an ambulance goes by, you hear like that. Okay, that's the Doppler effect. If it's the Doppler effect of an electromagnetic wave, like light, you're going to get a shift in the frequency of the electromagnetic wave, which corresponds to color. So, okay. So, if the source of the wave and the observer of the wave are separating, okay, the observed frequency is going to be lower than the actual emitted frequency. It's going to go down, okay? That's why once the ambulance passes you, you hear a lower pitch because it's going away from you. You, the observer, the ambulance, the source. If the source and the observer are nearing each other, then the observed frequency is going to go up. All right? So that's basically, we can do just a little example. What if the source of a wave is right here and it's headed this way at, let's say 50 meters per second, and the observer is over here and they're moving this way at 150 meters per second? Well, because the observer is in front of the source and the observer is moving faster than the source, they're actually going to be getting further apart as time goes on. So that means that the observed frequency is going to be shifted down. Okay. So we talked about this a little bit last year, and this year you have to go a bit further because we're going to actually learn the Doppler effect equation. So you might remember this equation: V equals lambda F. Hopefully you remember that. Okay. And if we take that and we divide both sides by lambda, we're going to get that frequency equals V over lambda. Okay? Now, basically, when the source and the observer are in relative motion, it plays around with both of these factors. Okay? If the observer of a wave is moving, then they're going to see the wave as traveling at a different speed. Okay? So the speed of a wave, the apparent speed of a wave, is affected by the observer's motion. You can imagine if I yelled at you, I'm sending a wave towards you at 340 meters per second, the speed of sound. If you were running away from me at 340 meters per second, you're going to see the wave as stationary because you're the same, you and the wave are not getting any closer together or further apart. So similarly, if I were to yell at you, I'm sending a wave towards you at 340 meters per second. If you were to run towards me at 340 meters per second, you would see sound as approaching you at 680 meters per second. So that's the observer's motion affects the wave speed, apparent wave speed. The wavelength is affected by the source's motion. Okay. If I think about if this is the source of a wave and it's emitting waves and the source is stationary, then the waves that come out are just going to be concentric circles. They're just going to go like this. Okay. So it just kind of looks like a bullseye. These are the waves going out, just like ripples in a pond. But if the source is moving, so let's say the source is moving to the right, then the circles aren't concentric anymore. So you get maybe some waves that look like this. Like this. So you can see that the wavelength is now shorter on the leading side, and the wavelength is longer on the trailing side of the source. Okay? All right. So now I can give you the actual equation. Okay? So let me shift a piece of paper. The observed frequency is equal to the emitted frequency times the quantity velocity of the wave plus or minus the velocity of the observer divided by the velocity of the wave plus or minus the velocity of the source. So basically the observed frequency is the emitted frequency times a correction factor. Now, what if the source and the observer are both stationary? What if they both have a velocity of 0? Then you would have the correction factor would be velocity of the wave divided by velocity of the wave. So you would just get 1 for the correction factor, and you get observed frequency is equal to the emitted frequency. But if they're in relative motion, then this is going to change things. You can see that the observer's motion is on the numerator, because remember how the observer's motion affects the velocity, which is on the numerator. Okay, so that's where that comes from. The source's velocity is in the denominator, because you can see in this equation I said that lambda is affected by the source's motion. Okay? I appreciate that there are 6 of you watching. Thank you. Now you have to choose a plus or a minus, just depending on the situation. So this is best. This is going to be best if we just do an example. Okay. Let's go to this example right here. So let's actually calculate what is the observed frequency in this case. All right. So carrying down the numbers from that example, and let's assume that this is with sound waves. Sound waves have the velocity of the wave is 340 meters per second. Okay? And by the way, let's say that the emitted frequency is 1,000 hertz. Okay? So that's going to be our numbers. We want to figure out what is the observed frequency. And so the emitted frequency was 1,000. The velocity of the wave, we're talking about sound, so that's 340. 340. The observer's velocity, oh, if I do this, you can see both. The observer's velocity is 50 meters per second. Okay. The source's velocity is, oh wait, I messed it up. The observer's velocity is 150. The source's velocity is 50. So now we have to choose the signs. So let's think about it. The source is moving closer to the observer, or wants to move closer to the observer. So let's imagine that the observer was not moving. The source is moving towards the observer. That motion by itself would tend to shift the frequency up. So when we have the option of a plus or a minus, we want to choose the option that's going to make the observed frequency bigger. Now see how the 50 is in the denominator, and we want to make the denominator, to make the observed frequency bigger, we want to make the denominator smaller. So I'm going to choose the minus sign. That would tend to shift the frequency up. To figure out whether it's a plus or minus in the numerator here, we ignore the source's motion, and we just see that the source, or the observer, is moving away from the source. That would tend to shift the frequency down, that motion in and of itself. So if I want to shift the frequency down, then I better put a minus sign there, because that makes the numerator smaller, which makes the fraction smaller. So the observed frequency would be that many hertz, and I can't find my calculator, so I don't know what it is. Okay? I did want to talk just very briefly about the Doppler effect for light. And for light, the speed of the wave is c, which is 3 times 10 to the 8th meters per second. Okay. 3 times 10 to the 8th meters per second. And typically speaking, your observer and your source, both of those things, are going to be moving much, much slower compared to the speed of light. And so in this case, it's actually, you can do an approximate equation which says that the shift in frequency, so the shift in frequency is equal to the emitted frequency times the relative velocity over the speed of light. So let's do an example with that. An example with that would be, let's suppose that, I don't know, a quasar emits light of frequency let's say 9.5 times 10 to the 15th hertz. Okay. The quasar is receding, so it's going away from you, which means that the frequency is going to be shifted down. The quasar is receding at a velocity of 0.4 times 10 to the 8th meters per second. Okay? And so we want to know, what is the observed frequency? So I would just use my formula for the change in frequency. The emitted frequency is 9.5 times 10 to the 15th. And then V over C is going to be 0.4 times 10 to the 8th divided by 3 times 10 to the 8th. Now, because the quasar is receding, the change in frequency is going to be towards lower frequencies. So I'll put a minus sign in there. And basically the observed frequency, so it's that many hertz is the shift in frequency. The observed frequency would just be the emitted frequency plus delta F. Okay? So this is an equation that only applies for light, for electromagnetic waves, and it's an approximate equation, but it's really, really good unless the thing is going close to the speed of light. So that is the extra IB Physics HL lesson. I hope you were able to follow along, and have a good night.